All right, so let me make a start on lesson 14. So I'm going to go just through as much as I can. We'll talk about the Token 2022 program. So, as I've said before, the token program, I mean, it's fine as far as it goes, but it was created fairly early on. And at the time, I guess people didn't know how, how these things would be used. And so over time, since then, we've realized that there are extra things that we would like to do. And so there's extra functionality we want to add. And that's the point of the Token 2022 program. Now, to make it backwards compatible, what they've tried to do is to make the data layout in accounts the same as for the token program, which makes a lot of sense. So they're just extending the data area effectively in the account. There's links there to the. Let me just I was check that actually. There's links to documentation. Um, yeah. So yeah, you can have a look through that. But I'll take you through some of the details. So they they want to add extra functionality, and this means adding extra fields into some of the accounts. So on the Mint account, they've got the possibility of adding transfer fees. So that it means when you do a transfer, then there'll be a fee associated to that, which will be held by a special account. The closing Mint. Um, Yeah. So you need to you can yeah, close the mint. You can stop that from proceeding, but you need to set that up before initializing the mint. Also, the possibility of interest-bearing tokens. So that could be great if you want to have a token that has an interest rate associated with it. And then the non-transferable tokens, or people sometimes call these soul-bound tokens. The idea is that once they've been minted, then they cannot be transferred elsewhere. So the use cases for that tend to be around maybe identity or showing something that the person has done, showing they've reached a certain level, that kind of thing. Then moving to the token account. So remember, the token account itself is the one that is specific to a particular holder of tokens. We have the possibility of some type of memo being required on incoming transfers. The immutable ownership, yeah, means that you can't change the ownership of the account, and that's used by the associated token account program. Also, the default account state, this is to put the account into a state when it's initially minted. So, for example, if you want something to be frozen initially, then you can set it up in that way. And the permanent delegate, this is to add a bit more functionality to the things that we can do with delegation because that was sort of fairly limited. So with the permanent delegate, that means then they can have unlimited privileges over the account for that particular token. Okay. Oh, did I have I skipped something there? No, that's it. Okay. So that's some of the extensions for Token 2022. Also, there's things about confidential tokens that I'll come on to in a moment. Next, I just want to cover a few projects around layer 2 and interoperability. This is a little bit unusual on Solana, or Solana is a little bit unusual because the way that Solana was designed and the way that they've thought about scalability has been to focus on changing the layer one. So making the layer one as efficient as possible. And we've talked about all of those types of innovations. So there's been less motivation to have layer two solutions in the Solana ecosystem. There really hasn't been the need because the layer twos tend to be created to provide scalability, and for Solana, we've focused on the layer ones for that. But having said that, then uh, there are some projects that do this, but maybe with less focus on scalability and allowing other types of functionality. So we'll just talk about those. first one here, Neon EVM. So this is to provide a an EVM compatible environment, but on Solana. So this would be useful if you're a developer that is useful to working on the EVM, if you're used to working with Solidity and all of the aspects around it of how the EVM works, and also you're used to the tools on Ethereum. This could be useful for you because you can use this. But it's actually on Solana, so you get the advantages of the scalability that Solana provides. Also, you get then you're part of the Solana ecosystem as well. But you've still got your project. Maybe you've ported a project from an EVM chain. So it's really useful for developers. Um, yeah, it's a diagram just to sort of show generally the same thing here. The idea that your front end, can interact with the normal EVM tools that you're used to, but actually the back end is making use of the Solana programs, etc. And this is a link here just showing you some of the things on the ecosystem that they have. I suppose yeah, Viper as well. So I forgot about Viper. If you've been coding in Viper, then you can use that as well. As I said, you can use all the tools. There's compatibility with the RPC nodes and the general standards. So yeah, very useful if you want to port a project from an EVM chain over to Solana. That's a way of doing it. There's links there to some quick start docs as well. The next one here, Nitro SVM, is uh, kind of not the same. It's taking the idea of compatibility to the uh, Solana, so to the sea-level virtual machine, and then doing that on Cosmos. So Cosmos is a project that allows interoperability. It allows chains to connect to each other in a structured way. And this is called IBC. And so one of the chains that's been built with that is Nitro SVM. So now you have something like Solana, so you can run your programs on this. It's compatible to the SVM, but then also you can interact with other chains via uh, the inter-blockchain communication protocol that Cosmos supplies. Okay, and there's links there if you want to have a look at that. And then the final one here, layer N, is this is more similar to the types of sort of layer 2 approaches that you see on the sort of the Ethereum ecosystem, for example. The idea that it is providing an extra layer and that then interacts with the layer 1. The With this though, you get this can be optimized even further for execution. And then they've got the idea of making specialized chains as well. So you could have chains specialized for different types of applications, which can then fit in, which will then interact with the layer N, which will then interact with Solana. Okay, so that's more of a sort of a traditional architecture of sort of the layer 2, layer 3 type of architecture approach. Okay, now similar to that, we also have Eclipse, and again, really looking at the idea of app-specific chains. This is to show this diagram is showing some of the on the left-hand side here. We've got some of the different concerns that are associated with a particular blockchain. And the first column here really is saying, the initial design is for monolithic Solana. So it's providing all of those services. And but then what it's trying to show is that you can break this out and have some of them done elsewhere. So you've got the some different possibilities here, such as having an app chain being used for execution. Etc. And yeah, but with all of them, they're still relying on Solana to implement the consensus and data availability. Uh, this looks very similar to what you saw with layer N there, but oh yeah, sorry. There is the possibility of moving the consensus and data availability elsewhere because you can connect then to EigenLayer or Celestia, etc. So that's again quite common in the sort of layer 2, layer 3 ideas and data availability ideas that you get on blockchains generally. Okay. So got lots of possibilities if you want to try these out. If you want to have something maybe more specialized, but still be within the Solana ecosystem, then you've got these possibilities here. Okay. I just provided a link here to about debugging Solana programs. It's um, let me just show you that. It's in the Solana cookbook. So it just takes you through some of it we've spoken about already, and it's looking at things like the local validator node. But also remember that there's uh, yeah, I think maybe it was last week we talked about some of the alternatives to that as well. We looked at the bank's client, etc. So that's also possible. But if you want details of debugging, then there's some useful ideas there. Okay. Now, Pinocchio, and this kind of fits, I guess, maybe maybe in between the sort of native Rust way of developing and Anchor. It's an alternative to each. It's, I think, designed for making small, very efficient programs. And yeah, the idea where you think that performance is going to be critical. Also, they have the idea that there's you have no dependencies. You're not depending on other libraries, and you're not relying on the standard Rust library as well. So again, this helps with uh, the the um, the efficiency of it and the fact that it ends up being quite small. Um, Yep. So the idea of not having dependencies is yeah is good. Yeah, you're not reliant on things that could potentially break, and also you end up it's more self-contained, it's much smaller. They have this thing about entry points. So we've got some examples in a second, which you can use. There are different ways to specify the entry point and different ways that the macro works that sort of provides the inputs to the entry point, and that can make things more efficient as well, particularly if the what you're passing into the program is fairly small. They have other techniques. This zero copy is an optimization technique to reduce memory usage. Remember, this type of thing could well be useful because as well as restricting the amount of compute that we do, the compute units, there are restrictions on the amount of memory that your program can use. So if you're having problems, then this may be something that will be useful for you. Okay, and then they've got yeah various utilities to help you as well. So just to give you an idea of some of these, the the entry point we've already seen the entry point macro, but then Pinocchio adds their own uh, uh, one for this to make it more efficient. This is just the normal one, I think. So yeah, this should look very similar to the things you've been doing before. And yeah, as usual, you put your business logic in. And then they have the lazy one as well. The I think if yeah, the point is that if you are doing the entry point on some very small inputs, it makes sense to use that. It's more efficient. So, for example, when we first looked at the entry point, we first looked at programs, and we had very very simple things. That would be the kind of thing where this would make more sense. And then moving on, sort of through the program flow, we if you look at how instruction data is handled, they also you have to do this yourself. So this is not like Anchor where it sort of handles all of that for you. You This is more like the native Rust implementation where you have to work out details of the instruction. And again, this should look familiar because we had an example from the token program where we were looking at different types of instructions and matching on those, and then doing different things. I think we had a mint instruction we were matching on. So similarly, you have to do that with Pinocchio as well. A you would read maybe the first byte, and then from that match to uh, do a particular instruction. So you can see here. Uh, Also with accounts, you have to do this yourself. So again, it's not like Anchor where we have the context to help us with that. And this example here, sorry, at the beginning, is going through the accounts that we get in our array. So we get our iterators to those, and then we are pulling the different accounts out. We're doing some checks as well, checking that the owner is the signer, etc., and checking that the account is owned by the program, etc. So that again should look familiar to you. But yeah, if you're using Pinocchio, you need to do that. Uh, they help you out with cross-program invocation. So here's an example where we want to get the token program to transfer tokens. So what we need to do is to create an instruction to actually do that, and then that needs the accounts that are going to be involved. So we're setting those up here. And then once we've got that, once we've assembled the transfer instruction, then we can use that, we can invoke that and pass in the accounts that need to be transferred to the program. And that will transfer to the token program and yeah, do whatever that's going to do, wants to do. So overall, it's something you can use if you want to maybe get better optimization, or you want to have more control, but it is lower level than say Anchor. So Anchor is perhaps a better choice just for more general programs, and if you are certainly beginning and just getting used to the environment, then it makes a lot more sense there. All right. So yeah, I said that the another one of the areas of the Token 2022 program is the confidential token extension, and I've got some notes here that goes through uh, quite at length. So I perhaps won't go through all of this, but it's to try to give you an idea of what is needed and perhaps some of the pitfalls and the difficulties associated with confidential tokens generally. Um, they're not an easy thing to design and to develop, and I mean, partly they go against some of the aspects that we expect in blockchain. With blockchains, generally, we're thinking about, well, we should have everything being very transparent. And so to have something confidential in there is a little bit difficult to fit that in. But people have done that. And there's, for example, with, one of the earliest examples is Zcash, where they managed to separate out so the aspects that are needed, um, where the blockchain, we want some visibility. We want and we typically say we want to be able to see all the data because we want to be able to check that things are being done correctly. Say a transfer is being done correctly. But actually, in order to know that, we don't have to have all of the data. We don't have to see all of the data. But we do need something. And with the case of Zcash, they create a zero knowledge proof within the system that provides that assurance that things are working correctly. And then because they've done that, then they can use techniques to hide details of the transfers. So Solana's thinking a similar idea with the idea of the confidential tokens, but how to do that is quite difficult. I mean, the typical approach, if you wanting confidentiality, is to use some form of encryption. So this is talking about what you could the approach you could take to do that. So, for example, we could try to encrypt balances before we store them. and uh, similarly, we could try to encrypt amounts that are being transferred. The That is good, yeah, that gives us the confidentiality that we want. But then we need the program that's doing that's processing this data has the problem that it is having to work on encrypted data. And you'd think, well, that's not going to work because the data is encrypted. We can't just do our normal addition and subtractions, all those kind of things. We can't do that on encrypted data, but actually there are ways that we can do that. So this is bringing in the idea of homomorphic encryption schemes, where we can do simple operations on encrypted data and they still make sense. So, for example, if you use the El-Gamal encryption scheme, then we can do additions and subtractions on the encrypted data, which is the kind of thing that we want to do when our token program is processing data and processing balances, adding them and subtracting them, etc. So there is a possibility there. That's the kind of thing that we can do. So that gives us a direction that we can go in and some techniques that we can use. So I've got some few details there. But the approach that tends to be taken, and again, looking back at Zcash, what they did or what they had to do was to then use zero knowledge proofs to show that the overall process has worked correctly. It may not be enough to use so these homomorphic encryption schemes. It may not be sufficient, but you may have to use other techniques as well, such as zero knowledge proofs, to then show that the whole process was done correctly. And then people, validators, etc., can check the proof and can be confident about that. And the point about the zero knowledge proofs is the zero knowledge aspect and the fact that these proofs are created with private inputs, and then when we're checking them, we don't get to learn what those inputs are. We just know that the proof is correct. So that's what this is trying to do. And some of the other aspects of this that are useful from something like this, if if you're thinking about using this, for example, with a maybe a central bank currency. And this is an example that I've come across where I've spoken to banks who have wanted to have confidential tokens. They've been okay with the idea that their customers could have confidential tokens and that the people in general wouldn't be able to see what that person's balance was. But then they do require the idea of a global auditor, somebody who can go in and actually look at and see the details of these tokens, so that they can check whether there's sort of money laundering happening, that kind of thing. So, it's kind of the idea of confidential token, but then in addition to that, we want the idea of a global auditor in certain circumstances, because we want the compliance and the regulation schemes as well. So that's what the thing about the global auditor is there. Now, one problem with this or implementing this approach is that if you are creating proofs of the that a transfer was done correctly, that the inputs that proof are going to involve a balance, and this then will get this will then get validated, and we could use that balance as an input. But that proof will not work if the balance has changed because the proof was very specific to a certain balance. And so someone malicious could try to prevent these proofs working by continually changing the balance on an account, potentially by a very small amount, but just any change whatsoever would uh, cause problems when you're creating and validating proofs. And so to prevent that, they have the idea that the balances there would be sort of separated out into the pending balance and an available balance, and you would create your proof from the available balance before you apply any changes, which is the pending balance. Okay. a little bit there about zero knowledge proofs. I won't go through all of that as well, but you can certainly read that if you want to. So let's go back to look at Anchor again, and I want to talk about uh, program design and application design. And one of the best examples, I think, certainly is, in terms of a simple example, um, when you're looking at program design, is something like a simple game like rock, paper, scissors, because this illustrates quite a few of the areas that are potentially difficult to implement in on-chain games. And so if you get the hang of this and you work out techniques of how to do this, and those techniques and those patterns may be useful for you elsewhere. So I want you to imagine that we want to write a program to to allow people to play the rock, paper, scissors game. And so if this is on chain, then what that means is that our two players are going to take turns to present either rock, paper, or scissors, and then the program itself is going to check and see which one of the players wins that. Okay. Um, a good starting point when you're designing games is to think about some of the accounts involved. So here's a an account diagram to show you where we would where we will be storing data. In this case, it's very simple. We've got a program that is going to own a game account. So this is where we can store the data for a game. Then player one and player two are going to be involved. Their accounts are going to be used because they're going to be sending in transactions to illustrate or to make their move to do their turn. So that's going to their details are going to be used, and that's potentially going to go into the game account as well. Uh, so if we think about the flow of the game, then it may be useful to think about it maybe as a state machine, that kind of thing, to think of the different points in the game that are relevant. So we're going to have one that is going to be we're going to have the new game state where everything has been initialized, and for that, we need to set up some data in our game account. And this gives you an idea of the data that we're going to need to hold in the game account overall. So this is going to be there for all aspects of the game. But what you can see is that so we have some details of the players. Then we have these things in the hands, or these are the turns that are involved. And we've got these a couple of places. I'll explain why in a second. Um, we also want something. This flag there is to show that somebody is uh, has provided details, so they've finished their turn effectively. And we also want to hold some details of the winner as well. So why have we got these hashes of hands and hands with salt, etc.? Well, the the first thing to think about is if you're playing a game and there needs to be some secrecy, then this is not easy to implement on blockchain because people can see the transactions. So if we didn't obfuscate the details of each turn, then the other player could see what the each player is doing, and they could effectively cheat. They would know exactly which hand to play. So it would be a trivial thing to win at the game. So the way we can get around that, a very standard way to do that, is the idea of a commit reveal scheme where a player will commit to a certain turn. So in this case, to rock, paper, or scissors. And then there will be something that obfuscates that. And then at a later point, they reveal what they played. So once both players have committed to their turns, then both players will reveal what those turns were, what those hands were, and then the program can work out which of the players has won, depending on that. And an easy way to do a commit reveal scheme is to use a hash function. So the flow would be that after the game has been initialized and we've got everything set up, then the players will take it in turns to produce a hash of the hand that they want to play. So a hash of rock or hash of paper or hash of scissors. And then that will then later when both have been submitted, then they will produce the plain text version of that, and the program can work out the winner and can check that that was the thing that they committed to. So that's the first thing that you can do. So that will help obfuscate what is happening, but only so far because this is a very simple game and there are only three alternatives, then it would be simple for somebody to work out what the hashes of those were and then see from the hash that was actually implemented what was chosen as the hand. So you need to take it a little further by adding a salt. So this is some random value that you put in along with the thing that you chose. So you have, say, rock plus some random bytes, and then you would take a hash of that. And then at the reveal stage, you would reveal the rock plus these random bytes, and so that shows what you committed to. Okay. So that's the thing we would need to do. We also need a flag to say that things have been submitted, because another point with a game like this is that people could potentially cheat by um, just not playing. They could just not take their turn, or if they decide if they think they're going to lose, maybe they just wouldn't carry on. So we need something to know whether whether somebody's there's been a timeout, etc. So we need to know what state we are in the game. So that's why we need some flags involved as well. Uh, yeah, so this is just the details of the general flow for that. Okay. Oh, I don't know if I've got. Yeah, I didn't have any further detail, but um, that's the idea that the design that you could use. So I just remembered the details of this are actually in the repo. Let me quickly uh, find that for you. Sorry, we do have an implementation of this. If I can. Um, to find it for you. Mm. Mm. Sorry, probably get up. I'll get it in a second. Please bear with me. Yeah. So, in examples, anchor, yeah, example number two, we've got an implementation here of a rock, paper, scissors game. So this is really implementing just what I said, but doing it in Anchor, setting up the accounts as we mentioned. Sorry, the accounts are not all in the same place here. Yeah, here you go. Here's the game account. So this is where we're storing all the data for the game. So just those things that I mentioned. We also have some errors as well there, which is useful. We also need the something to say the result of the hand, so we can use an enum for that there. And then we've got the various contexts, as you can see here. So when when we're creating a new game, we need to set up the account, the game account. We also need the players. We allow a player to set up the game, so they need to be signing for that because there's a new account being set up there. And this, what have we got? yeah, this is where the what we do when we're actually taking a turn. We need the game account again, and we need details of the player. So that's the context there. Okay. All right. And then in terms of the implementation, I think it's fairly straightforward. When we create a new game, we are setting up the details to put into the game account, basic details of the different players. The way that the new game is created, you're assuming that one of the players is creating the new game, so that they're regarded as player one, and then they have to pass in the address of player two, so that can go in the account. Then once that's happened, then they can decide to place their do their first turn, place the hash. So that's what we've got here, and that needs the game account that we set up so that the details can go in there. Um, and then finally, uh, yeah, we need to place the hand as well. Um, and then we've got implementations here of how we can check the results. So you've got uh, the we check the different hands. We've got a scheme to decode that, and we've got this idea of which hand will beat which other hand. Okay, all right. So that's an example, the rock paper scissors example. The I wanted to show you as well a PDA example in Anchor. So this one, yeah, from the Anchor docs. Um, we've got some different schemes here. If you remember when I spoke about PDAs before, I said that you need to design the scheme that the of the seeds that are going to be used. So this is what we've got shown here for different examples of uh, different seeds. You've got some potential implementations here. So the first one, we're not actually providing any. So that would be where you're just going to create one PDA for that particular program, and you never need more than one. Um, or for example, here this you've got a just some kind of string for that. But then you may want to have different. So the second one allows you to create new PDAs for that program, so you can create more than one. But it's yeah, you'd have to have different things coded there. This one is where is dynamic because you get the seed to specify a particular type of program, and then you're also dependent upon the signer as well, their key. So that's going to give you a different PDA for each person who is setting the transaction. Okay. Yep. So there's some details there of how you can do that within Anchor. Although yeah, we did see this already. Actually, I guess you've probably already seen this. So um, yeah, you don't need to. Yeah. Then also the CPI in Anchor, I don't think we saw this in the example that we had. So it's worth just having an idea of this. And what this is doing is it wants to do a transfer. So it wants to get the system program to do a transfer of Sol. So which is going to be a function within the system program. So you need if you're calling that from your own program, then it needs to be a CPI that you're going to use for that. So this is showing you the accounts that we need in order to do that. So we need the to and from accounts, obviously, but we also need the system program. So we need that, which we've got here as the program ID for that, and then we can we can set up a context here for the CPI, and then we can uh, uh, use well, do that. We can use the transfer with that context and the amount, and then um, hopefully that will work. If not, then you've got the question mark here to throw the error back up the stack. Okay. Um, Yep, so you've got more examples there if you want to have a look at those. But yeah, it's worth we hadn't covered or we hadn't seen that in Anchor, I don't think. So have a look at those examples and you should be able to work out how to do it. It's really just I mean this is using the transfer on the system program, but it's the same idea of if you're doing it with other programs as well, with other functions. What time have we got? We've probably got time. Let me just quickly have a look. What else we need to cover today? Okay, I think we'll have a look at some more of the examples as well because it's going to be quite useful looking at more complex examples. And really, the rest of the notes for today are um, oh yeah are very straightforward. Probably don't need too much explanation. So. This is showing you how to build an election program. So again, it's a very standard kind of thing, something that there's a good use case on blockchains for doing voting, but it's not necessarily a simple thing to implement. So there's details here of how to do that, and nicely they've got a diagram here of the accounts that they're going to use, and hopefully the GitHub is still there. Yeah, okay. So they've got uh, the details of the program, so we can have a look at that as well in a second. Let me get rid of that. Sorry. Okay, so looking at the accounts, and I think yeah, it definitely helps if you work out the accounts that you're going to use. It'll also help you think about the program flow as well. So we've we've got the uh, an, an account for the election as a whole. So that kind of makes sense. That's something we're probably going to want to have with any program is to have an account for the program. So that's uh, yeah, that makes sense. Which has got some general details such as the number of candidates. We've got the idea of there being stages within our program, so we've got an enum for that. And then we've got details of the winners as well. Um, this does lend itself quite nicely to the state machine idea as well. They've got the idea that the election will be in a different state and you can do certain things in one state but not in another. So that's we've got the details held there within the election account. Then we have we need details then also of candidates and voting. So we've got a couple for the candidate. One, we need a some identity account, which is going to give us a number and the address for the candidate. And for for these, it makes sense that these are PDAs. So the the PDA is going for the identity account is going to be based on the candidate's public key, but also on the election public key because this is specific to a certain election and specific to a certain candidate. So that's the design of that. Um, Also, the do we want other details about the candidate? So again, we've got the PDA, which is dependent upon their ID from the identity account that we've got set up, plus the election account public key, because again, it's specific to an election. So that, yeah, that's then tied to the details in the identity account and the election account. Then that gives us our candidates. Then the votes themselves. Well, we need a vote account. Again, we're going to use a PDA for this. This has a string in it to show that it's to do with which is for voting, and we are going to use the voters public key and then the election account. So what this is doing is making the address that is used here dependent upon the election account, which makes sense. You want it to be specific to this election, but also it's dependent upon the voter's public key. Now, what that means, because that's all the dependencies that we have within the seed. What this means is that if we tried to create another account for this particular voter for this account, well, it would come up with the same address. So this is ensuring that each voter will only have one account for the vote account. So it's adding by the design of the seeds within the PDA, it's providing a constraint that makes sense for the way that the program is intended to work. So that's quite a nice feature there. Yeah. There's details here of the flow as well. I don't know if we need to go through this too much. Yeah, this is the initial setting up of the election. As you expect, there's a create election context that's going to be used. Here we've got the context you can see here. So this is setting up an account for the election account that's going to hold the details of the election. And then that you can see how they've worked out the space that is needed in that account, remembering that we need to annotate at the front of that for the discriminator. And that's going to give us our election data. We also we also need the account from the signer and the system program as well. So very common, you've seen all of that before. Here is the structure of our election data, which just is similar to what you saw in the diagram as well. As I said, we've got this idea of there being election stages, and so we've got three here: the application, voting, and closed. Okay, and we've got the possibility of error codes there as well. Details. I don't know if I'm sure how much we want to go through with this, but yeah, let's keep going through it. So we've got this. We need to be able to do things such as applying to be a candidate. So we've got the apply context here. So you can see, and remember, this is going to be a PDA. We're going to make it specific to this particular election. So that's why we've got the election account key as one of the seeds. It needs to be specific to the candidate applying. So we need their details here. And then we are making this different from any other type of PDA that would have a similar setup by saying this is going to be about the candidate. So we've got a string there for that byte string. So that will set up the PDA for this particular candidate when they apply, and that's available to us there. And we have a check that this is in the application stage still of the election, so we need to do that. If we get past that, everything's okay, then we can bump the number of candidates by one, and we can set up details of the ID. So this is where we're tying the different accounts together, the identity account, and we're putting that into the election account for this particular election. Okay. And once they've applied, then they can we can do the register. So a similar sort of thing again. This is going back to the setting up the candidate data account. So yeah, uh, that's the register. Again, we have to set up the PDA and we have seeds for that. We've already got the identity, and again, we want to use the details of the election account as well. So that's included there. And we can, yeah, those are all the accounts that are needed for that. And that gives us uh, the candidate data. Okay. Um, this is about changing the stage of the election, how we move between different stages. So this uh, takes in the stage and allows us to move to a new stage. So you can see there's matching. So this is where we are constraining the way that we can move between the stages. So once uh, we we say which new stage we want, then it's going to do various things. So such as if we're moving to the voting stage, then it's going to close applications um, or voting, etc. So that's how we move between the stages. Um, and voting, uh, when we are when we want to vote, we need the vote account for a particular voter. So again, we're going to set that up to PDA. So we need the seeds, and the way that this has been designed, this means that when we're deriving this, for every voter, we will only be able to derive one address because it's dependent only on the signer key and the election, and then this voter string here. So we're always going to get, for one voter, we're always going to get the same address when we derive the PDA. So that's, yeah, constraint added there. Uh, yeah, so that's that. So we can uh, we set up that we can get the election account as well. We need that. We can use that to check the stage of the election. So we make sure that we're able to vote at this particular stage, and then we can actually apply the votes. So apply the votes to a particular candidate there. Okay. Okay, so I hope that made sense. It's a slightly more, perhaps a slightly more complex example than the lottery example we had earlier on. But again, I think it's quite useful to see how you can design these things and working out the accounts that are going to be needed, first of all, is useful. Uh, and also the point with the thinking about the seeds that are going to be used and the scheme that you're going to use for the seeds is useful. And not just because it has to be correct, or things have to be unique, but it may be that the way you design it can also take care of some aspects of the sort of semantics of the program, such as with the voting, to allow a voter to only have one account. So it's worthwhile thinking about that, planning that out. Okay. All right, so that was details of election, and yeah, there's the repo link to that as well. We can also take a quick look at the NFT example. Let me just get rid of some of these. Don't need. So yeah, another. This is a much more complex example, actually. This one, but again, yeah, they've got details of that. You can see it's they've the model is more complex for this one. Um, I don't know if we want to go through all this. Maybe it's too much to go through it once. This diagram here actually is just showing you again how NFTs work in general. The or if you look at something like the Metaplex, um, what they did with their standard for metadata. This is really showing details about that and how that maps to something in a collection. So this is kind of showing you with a specific use case in mind and how you can create all of that. So what this is showing is that we you can create the NFTs and remember that when we're doing this, we're still using the token program. So we've still got that basic stuff there, but then we've got extra things as well. So we've got these NFTs being created with the suppliers being one with zero decimals. Um, that's going to result when it's minted in a token account with an amount equal to one. But then we have the metadata account that is set up as well. And for an NFT collection, then you're going to want collection details in there. Excuse me. Um, yeah. So that's useful to have a look at. I think this is going to be too complex to go through. But yeah, if you're interested, if you want to do something similar, it may be a good article to have a read through if you're thinking for your final project of doing something similar. Do check that out. Okay. Um, okay. I'll just mention these quickly. Just you may come across this, so it may be useful. The idea of version transactions. So there was oh, there's potential problems. Solana, it needs to be performant. We want it to be fast and efficient and scalable, and so that does mean that there are potentially some restrictions placed on the way that this system works. And one of these is that the size of the messages that are passed around the network needs to be restricted. There needs to be some restriction on the size of that. Uh, Otherwise, yeah, the network would become very slow. What that means is that you cannot have more than 35 accounts in a single transaction, which it may sound like a lot, but then if you think of some of the complex or the more complex projects, such as we saw with the when we tried to do a swap. We looked at the swap program and the number of accounts that were involved in doing that. You can see that it's you can get up to 35 quite quickly with that. So the way around that they've got is to allow lookup tables to be used so that we can put addresses in those. But if we do that, that means we have to have a new format of transactions. The way that they can do that is that there's a byte that is um, sorry, yeah, they can do that using an index rather than a full address. Sorry, and so that's what will be used by the new transaction format, which is going to be is going to mean it's going to be smaller because we don't have the full address. We can just have an index. So that's going to make things um, going to mean the message is potentially much smaller. If we do that, though, we need to show that's what we're doing, that this is the new transaction type rather than the old one. And in order to signal that, what they've managed to do is they realized that there's a byte, sorry, there's a bit that isn't being used. And so they've sort of used that to say that it's the versioned yeah, it's the new type of transaction. Um, when we do this, there are still limitations, so we can do more than 35 accounts, which is our original limit. We can go up to 256, and the limit there is just because of the size of the data field that is holding the indexes there. Um, but yeah, 256 is probably going to be enough for most use cases. Um, you can't do um, you can't do any kind of recursive thing with all of this. That's the only depth you can go to. So yeah, you're going to be limited to 256. Um, yeah. Okay. So that's what version transactions are about. You may come across those. Um, okay. All right. Now, something that may be interesting to you if you've come to Solana from EVM chains is the possibility of using Solidity. So we have Solan available now, which has been a compiler has been written for the Solidity language to allow it to be used on Solana. But you do have to be very aware of what this actually gives you because it is we're still running within the SVM. So the programming model is still the same. We still have accounts and programs, etc. It's not that we've got the EVM features. If you want that, then if you look back in today's notes, when I was speaking earlier about some possibilities for you there, there are this project that you can use there. But what this is saying is that rather than using Rust, we could use Solidity, but we still end up with the same program. We still have to think about programs and accounts, etc. Uh, but it's been done. So we do have to do extra things, but it does mean that we can use the Solidity language. What it looks like is this. We have to add annotations to the code so that it will understand some of the details that we need that are just not provided as part of Solidity code. So, for example, we've got because this is setting up a program, we need to say who's going to be paying for this. So we need a payer field there. Um, this we also need, yeah, we need the program ID as well, as you can see there. So that's these things have to be added. This is a working program, I think. It is very simple. It just flips a bit. So you've got that being stored there, and then the functions just allow you to flip that and then get the result. Um, the 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 data that it holds, so this state that is held, will then be put in. That will be in an account. So obviously we that's not going to go into the program. Programs are stateless, so that an account will be created for that. Um, there's details of how to install it. Sorry, that's not formatted very well, but there's details of how to install that, and you can set this up um, in Anchor as well. So when normally we would do the anchor init and a project name to set up a Rust-based project, but you can use the Solidity flag to get a Solidity-based one, and this gives you that code as an example. If you want to look at how it works in more detail, you can look through the test code that is provided as well. I don't know if there's anything there that I want to point out. It's really just calling the various functions. Uh, yeah, as you can see there, and testing that the flip works, and that is then printing out the state to show you that that's all worked. Okay. Um, another example. Sorry, doesn't this is not scrolling very well. Another example we've got here is of creating a token. Um, the but this still needs uh, to follow the same approach we have with the token program. So we still need the idea of all of the fields that we have in the Mint account for the token program, and then we can use effectively CPI here to to create the Mint program, as you can see there. So we need uh, the SBL token program, and then that can do the create mint based on these details that we're sending it as well. Also, here we've got a using metadata. So the metadata standard we looked at, you can add all of those details in as well. Okay. So yeah, so it is possible, but as you can see, it's still you're doing the same thing that you still have to do a program, you still have to do accounts. So all that's really different is the language. So it depends whether you want to use Rust or you want to use Solidity. Really, that's the advantage to that. Okay. Uh, there are other possibilities as well. Again, we haven't covered this one, but you will have seen when you looked at the Solana playground that there was the possibility of writing your program in Python. So that's possible as well. And yeah, there's details of how to do that there. Okay, I'll just quickly, well, I'm not sure if we need to go through much of this actually. This was, again, something that somebody asked for to know the requirements to run a validator on Solana. The requirements are quite high. The hardware needed is, yeah, so it needs lots of memory, as you can see there. Um, this, I took this, I think just a few months ago, so it's probably reasonably up to date. But it is, if you want to run a validator node, you are going to need, fairly uh, high-powered hardware, as you can see there. RPC node, well, yeah, some of it similar, but yeah. You also need reasonably good networking as well. If you're running as a validator, then you need to provide the stake for that, which is required every epoch. Um, this I don't know the current rate actually, but you can see the rough idea of what is needed for that. Um, but yeah, so you need to have a lot staked to do that, but that can be delegated as well. Uh, if you are running a validator, you will get Sol because of the staking reward and then some fees. So you'll get part of the transaction fee, and if you uh, if you're staking, sorry, if you're delegating, then you'll get something back from that. Um, the This is the inflation schedule. I haven't updated this lately, but I mean, this is presumably what is still happening. So, yeah, you get the idea that they are reducing the amount of rewards over time. I'm not sure where we are actually on this. Must be right about here somewhere. Okay, so that's a little bit about running a validator, if you're interested in that. We've got a tutorial for you to have to work through, which I think you is quite useful. We haven't said very much about this aspect of uh, development in that we haven't really spoken much about game development, but there's an example here that you can go through. Um, it Yeah, I think you can do this on the Solana playground as well. Yeah, you can. This one is designed to be done with Anchor, so it's got details. It takes you through. It's a very simple program, a very simple game, as you can see here. It's uh, moving, just something, yeah, printing things out to show the movement of your player. But yeah, it takes you through what you need to do. So do try this, and uh, the way it's set up, I think, is reasonably simple, reasonably straightforward. So you should be able to do that. You need to be thinking about just the things we've spoken about with Anchor, the idea of setting up a function, um, having some data defined, the definition of the data for in an account, and then the context that sort of puts those two things together. So as you can see here, we've got the initialize, setting up the game initially here. So you can see we've got a PDA being involved here. That's going to be the game account for a particular player, I guess. Um, yeah. Uh, and then it shows you how, once you've done that, then how you can actually play the game, moving in different directions, left and right, etc. So it's a very simple game, but yeah, do try it out, see what you think. Um, there's details here of once you've got the program okay, then there's details here of how to create the client. This is all shown uh, how to do this in the Solana playground. So this should be fairly straightforward there. Um, Although you obviously don't have to do it like that, but that's probably a good thing to do. Makes it nice and simple. Um, yeah, so have a go at that. Um, and then there's some, if you finish that, you've got more time, then we've got some extra articles for you to have a look at there. Okay. Um, so we've got a little bit more time. So I can just quickly make a start then on the tomorrow's topics. What I'll to start off talking about identity, it's good to have a look at some background and of look at decentralized identifiers. So there's a standard for these. It's not tied to blockchain specifically, although people have tended to associate the two because they are both decentralized. But decentralized identifiers and their standard does exist separately from blockchain, and there's a schema to show you how the standard for creating these and how that is done. What uh, is what this ends up being is that for a particular subject, so this is the person is who has the identity or the thing that has the identity, they will have a did. This could be um, this may refer to a document where there's more details, but it's going to get stored in some type of registry. This could be on blockchain, or it doesn't have to be, but there's just that can be stored, and there has to be some means to be able to get that. The It does follow this thing, which hopefully I'll have a bit more time to talk about, the idea of privacy by design, where when you're designing the data and how it is accessed and how it is used, that you use privacy as a default setting and have the ability to keep data private as a core part of the design. There's a link there to the principles about that, which is worth having a look at. I don't think I don't say enough about privacy really. I think I should say more about that. Um, but alongside DIDs, we have the idea of verifiable credentials, and these the idea behind this is quite applicable in another number of different areas. But the way is also works with decentralized identifiers is that it is some type of credential that you can verify with some cryptographic technique. And the what tends to happen if you for thinking of a use case, you could have something like a bank issuing a credential to say that the holder of that credential maybe has a bank account, um, and the bank could give that credential to the holder, who would keep that in some sort of wallet. That's the typical way that these things are used. And then this would be available or could be made available to a verifier. So somebody may come along and say, well, I want to know if you have a bank account. And so the holder could then present this credential to the verifier, who would be able to check that it is a valid credential. Because of the cryptography involved, they could check that. If that's going to be the case, then there does have to be some kind of link between the issuer and the verifier. They do need some kind of agreement on what the credential represents. So that's why we have this link here at the bottom with potentially, yeah, some type of data registry being involved. Again, this could be on blockchain, but it doesn't have to be. This is sort of agnostic as to the the architecture of that. But that's what verifiable credentials are about. You may well see more about those. Let me move on. I don't know why this is not working. Oh, there you go. I'll just quickly talk through some identity solutions that are available. Actually, I've said here these are on Solana. Most of these are also on multiple chains. So people tend to build these generally, not specifically to any chain. One of the uh, fairly old ones, I think, or yeah, original ones was Civic. Um, Again, you get this idea that there will be some kind of credential that could be stored within a wallet, and then can be presented. Um, and they have their own service to issue these and to show that they're valid. This is giving some ideas of the use cases for those. The idea that you could use it to show that you're a real person when playing a game, for example, or use it for access control or whatever. Also, it may be involved in compliance for different types of financial systems as well. Other ones, just mention quickly, there's BlockPass. I think a very similar idea. The Lit protocol. This is more about having security and privacy as well. But yeah, there's some document. Sorry, there's a link there to their docs that you can have a look at there. Okay, so there's some possibilities if you're thinking about identity solutions that you may find useful. Okay, we're out of time, so I'm going to finish there. Yeah, thanks. Bye bye.